Good day, everyone. I am pretty sure that we are all familiar with Albert Einstein. Albert Einstein was one of the scientists that introduced a lot of theories in the science world. In today's video presentation, we will be discussing some of the theories that Einstein introduced. Time dilation occurs when an object moves at high speeds, causing time to pass more slowly for it compared to a stationary observer. This was proven in the Hadron heating experiment, where atomic clocks of a fast-moving plane showed time loss compared to those on the ground. Einstein also introduced the concept of simultaneity, meaning events that seem simultaneous to an observer may appear different to another. This isn't because light changes speed, but because time itself is relative.
So now let's talk about Einstein's theory of general relativity. It redefined gravity not as force, but as the very shape of our universe itself. So in 1915, Einstein upgraded his special relativity theory and he included gravity, which are now called general relativity theory. Well, the reason was, the massive objects from space like stars and planets. He said that they doesn't pull things, instead they bend the very fabric of space-time itself and nearby objects move along in these curves. So in 1919, astronomers saw a starlight bend around the sun during an eclipse, just as Einstein predicted. Wow! So Einstein's theory turned gravity into geometry. Over 100 years later, it's still our best guide to understanding the cosmos. So, gravitational time dilation and frame dragging are also part of general relativity and will be talked.
Time dilation means time moves slower for someone moving very fast compared to someone standing still. The faster they move, the time slower for you to relative to someone at the rest. The experiments confirm to the replicating experiment. Using 4 atomic clock on the planes flying east lost time while the other one west gained time. Here's the other examples. Twin paradox. Do you hear that? Twin paradox using twin. The other twin fly to the surface at the speed of light while the other one is remain at Earth. So the one who flew from the surface of space, when he comes back, he's much younger. When the other one who stay at Earth become or has aged more. Simultaneity means the two events happening at the same time. For one person may not happen at the same time for someone else moving at a different speed. In other words, it depends on who is observing at the event and how they fast are moving. So here's the example. For example, I am in the sidewalk and I see both planes crashing. See now, here's the other one. For example, this is the train and it's moving up here. And you see the difference between those two. It shows that in this train, it shows that in this perspective, the one in the right shows the moving much faster than the other planes in this hand. So it shows the different motion and difference who observing.
Gravitational redshift happens when a light has to climb out of a strong gravitational field, like a near star or a black hole. As it moves away, it loses energy and its color shifts toward the red end of the spectrum. This shows that gravity can even affect light, stretching it and changing its appearance. Einstein's theory of general relativity says that gravity bends space and affects everything, even light. Scientists have tested gravitational redshift and found that it happens exactly as Einstein predicted. This effect is important for studying space and even used in GPS system to make sure satellite clocks and stays active.
Einstein's theory of general relativity has been instrumental in revolutionizing our understanding of the universe, and is also the very basis of modern cosmology and astrophysics. It explains how the universe expands and is an important criterion for the Big Bang model of universe formation. It has predicted many of the major cosmological phenomena that have now been observed, such as black holes, gravitational waves, and gravitational lensing. For some, this theory, especially general relativity's assumption of the Earth's motions and gravitational field, is even necessary for modern technologies such as GPS to operate correctly. But although general relativity makes good progress, it leaves much to be desired. In particular, what is dark energy and what lies behind a black hole's event horizon? Gerald Einstein proposed special relativity in the 1939, describing space and time without any kind of gravity. Both theories helped develop our understanding of the cosmos and open new areas of scientific exploration.
Before, people thought of space and time as fixed and unchanging. But with special relativity, which was introduced in 1905, it showed that both space and time can change depending on how fast people move. This means that time can be different for someone traveling at high speeds compared to someone at rest. In 1915, general relativity built on this idea and showed that gravity isn't a force, as we once thought, but it is caused by the way large objects bend the fabric of space and time around them. Einstein's theories show that gravity isn't just a force, as Newton had suggested before, but it is the result of massive objects bending the fabric of space-time, which completely change our understanding of how planets, stars, and light interact in space. So gravity is no longer just a pulling force, it's a distortion of space itself. Before, black holes were purely theoretical. However, general relativity predicted them as regions where space-time is curved so intensely that not even light can escape. This shifted our understanding of the universe, opening the door to the study of these extreme objects. General relativity also contributed to our understanding of the universe's expansion, because Einstein's equations predicted that the universe is dynamic and not static. This helped shape the modern Big Bang theory, showing that the universe began in a singularity and has been expanding ever since.
Einstein's theory of relativity completely changed science, changing how we understand space, time, and gravity. It didn't just reshape physics and astronomy, it also led to real-world applications like GPS, which relies on relativity to function accurately. More than that, these ideas gave us deeper understanding of the universe, showing that it's not static, but constantly changing, showing that the curvature of space and time, and even today, Einstein's principles continue to drive new discoveries, pushing us about the boundaries of what we know about the cosmos.
Einstein's theories of special and general relativity completely transformed their understanding of space, time, and gravity. Special relativity showed that time and space are not absolute but depend on the observer's motion. This introduced mind-bending concepts like time dilation, where time slows down for objects moving near the speed of light, and length contraction when fast-moving objects appear shorter. These ideas challenged classical physics and reshaped how we perceive motion, energy, and the structure of the universe. General relativity took this even further by redefining gravity as the bending of space-time rather than simple force. Massive objects like planets and stars create curves in space-time, affecting the paths of nearby objects. This theory not only explained previously unsolved mysteries like the Mercury's unusual orbit, but also predicted phenomena such as black holes and gravitational waves, both of which have been confirmed through modern experiments. By showing that space and time are flexible and shaped by gravity, Einstein's work provided a new foundation for modern physics and continued to influence our understanding of the cosmos. That will be all for our presentation. Thank you for listening and have a good day.